is going to have a number attached to it. It's going to have a value attached to it, called the p-value, probability value. So sometimes they are less than 5%. Well, sometimes they're less than 1%, sometimes they're less than 12%. They're always equal to something. I want you to look at that curve right there. This is essentially the same as my Advil curve. It represents usual heart rates. Usual heart rates. So here's average. I don't know what it is. It's average. It's something, whatever it is. And it's got standard errors around it. Just let me it's got a margin of error on both sides if you're dealing with a sample. Even if it's a population value, it's got a standard deviation. So the idea is, this is the number of beats per minute, your heart rate. And they can go off technically to infinity. I mean, technically, I guess past the point you're going to die because your heart's going to explode. And I guess technically it bottoms out down there at 0, in which case you're dead too. Heart rates get pretty low, especially if you do a lot of high aerobic activity. Lance Armstrong, I think years ago, his resting heart was something like 38 or 42 beats per minute, which is staggering. That's like corpse-like. Like you wake up in the morning, check your heart. Sometime in the morning, when you first wake up, check your heart rate. That's the best time to check it before you drink coffee, before you start like waking up. Check your heart rate and see what it is, and then check it later in the day and see how it fluctuates. It's amazing. It's amazing. So anyway, there are limits to how far it can go left and right, but mathematically there are not. It's infinite, as you guys said before. So here's average. Average. Here's elevated heart rates. Here's what caffeine you would expect caffeine to do, right? So let's suppose, here's your average heart rate of this cyclist, and you give him a caffeine pill, measure him later, and he ends up over here. Well, that's what you kind of expect that, right? You kind of expect it to go up. What if he ends up over here? Well, maybe you want to check on him and make sure he's okay. Maybe he's spiked so much now that he's going to pass out on the bike. Even on the little spin bikes they have down at Mazama, it says, you know, heart rate monitor's not always accurate. If you're feeling dizzy, stop. It only says 120. You might want to stop. You just vomit on yourself. So when you're over here, you're starting to get significantly high. Yes, significantly high. Okay, so suppose we give somebody caffeine, and this is their average, and they end up here. Did it lower their heart rate? Yeah. Say that again, Austin, with the same motion, the same sound. Did you see that? Why?
Because it's not enough to even measure.
Give me 2 words, both starting with S, that wrap up that whole perfectly. It's not statistically significant. Thank you. From now on, that will be called I love it. From now on, it has a dance. Yes. The non-statistical significant dance. Right? It's not statistically significant. Sure, it's below average, but it's not statistically significantly below average. It's the same I do when they say, holy crap, unemployment went from 7.8% to 7.9%. Ah! Yeah, so what? What's the margin of error? Oh, you didn't give me that. Oh, It's the same thing. It's exactly the same thing. You haven't proven to me that it's gotten far enough away from average to be worried about. Fair? How about now? It's good noises. Right? I'm not sure. The question then becomes, how far away do you have to go until it is statistically significant? Don't answer that! Because there is no perfect answer to that question. But there is an industry standard answer to that question, which is not perfect, but it's industry standard. And it's one of the interesting things. I have a quiz for that for you guys in like 3 or 4 weeks too. The industry standard cutoff, not saying it's the right cutoff for every case. The industry standard cutoff is once it goes below 5%. That's when you start doubting that it should even be on this curve anymore. And that's what happened in this article. They measured heart rate, and the heart rate was here at average, and it fell down to, I put it here, I didn't know exactly where it was because they didn't tell me. But it landed over here. Now, how do I know it landed over here? How do I know it landed over here? Well, they told me something, didn't they? They said the probability value was less than 5%. And you know, because of STANormal and the work we did back in 243, the very last quiz you guys ever did was all about this. I actually put the answer to this question on that quiz, knowing I'd see some of you again. I said, what's the probability Z is less than negative 1.645? Boom! Answer's 5%. Answer's 5%. Because that Z-score right there is negative 1.645. So if you fall below, you don't have to memorize, don't memorize that number. I've been talking about it for 20 years, so it's stuck in my head, kind of like my phone number. Don't worry about it. We'll come back to it. Negative 1.645. That means when we crunched our data, the z-score came in below that. Which means it's no longer close enough to average to be believing that it's on this normal heart rate curve. It's now more likely where? Say that again, nice and loud. On another curve, Emily. It's more likely on some other curve down here, more likely. Could we be wrong, and might it be on that curve? Of course, it might be on that curve because we may have just gotten outlier data, deviant data. Maybe these 9 dudes just had a weird fluke in their system that day. It's only 9 of them, right? There's going to be a wide margin of error regardless. So maybe they just had a goofy fluke, right? So what should we be doing with the study anyway? Replicating it and see if that shows up again. But based on these results right now, this is what we'd say. Our p-value came in under 5%. And you'd have to admit that it could have been a fluke. But it's more likely that we are not on this curve and more likely on some other curve. I'm 95% confident of that. Fair? See the mathematics and the kind of the word. Donnie, you brought up a very good point earlier about the reading and the consumption of this. You're not going to see this graph in the article. But this is what you have to process those words as. And I do agree, it becomes, I think we do our students a grave disservice in our Algebra 1 class, Algebra 2 classes by not making them read more. Here's an equation, solve it. No, the hell with that. Give me an equation and solve it. Here's a paragraph. I know you guys hated those, right? You hated reading, freaking story problems. That's the best part. That's what statistics is pulling that stuff out. Look at your exam, it's all text. How many numbers on that thing? It was like 12 numbers. And most of them were the numbers of the problems. Yes, right? You're not so sad, it's okay. Sorry. Let's get back to probability. So here is that p-value statement again, but written down in words. For those of you that don't like the picture, here's the words. I'm trying to hit it as many different ways as I can. The article itself, a new graph, and now the actual probability. What is the chance that we observed lowered heart rate data? Because we did, right? We observed lowered heart rate data. What's the chance that we observed that lowered heart rate data if caffeine isn't causing the lowering? Because that's that blue curve, right? That blue curve is caffeine is not lowering heart rate data, or is not lowering heart rate. That's the blue curve. The blue curve is caffeine is either keeping your heart rate the same or making it go higher. So that's what this right side is. Caffeine had no lowering effect. It's either going to keep it the same or it's going to raise it. That's what we would assume caffeine would do, yes? So what's the chance that caffeine lowers heart rate? Well, it's going to be less than 5% because it landed way over there on the curve. When you see these less than 5%, these very small p-values in the research, that's when you scratch your head and go, huh. It's like the opposite of, let's make up one for that too. If that's bigger than 5%, what should less than 5% be? Ooh, that's good. That's good. It's that, yes? That's the, I better take a look at that. And this is probably the most important thing I'll tell you today. Okay, I mentioned